Hello. Today we expand our review of the origins of the first law of thermodynamics, moving from a point mass to a macroscopic system. This requires us to introduce the concept of internal energy and define two types of ideal systems. You will recall from undergraduate thermo that there are closed systems, also called control masses, and open systems, also called control volumes. The main difference between the two is that the mass in a closed system is fixed. No mass can cross the system boundaries. In an open system, mass can cross the system boundaries. Since the first law is essentially a balance equation that keeps track of the flow of energy, it will have additional terms if mass is allowed to cross the system boundary because mass can carry energy. When we consider a macroscopic system, we have to take into account both the overall kinetic and potential energy of the system and the energy of the microscopic motion of the atoms and molecules that make up the mass of the system. Atoms can move depending on the environment they are in, and this leads to what we call translation. Molecules can translate as well, but since they have distributed mass, they can also rotate, and the individual atoms that make up the molecule can vibrate with respect to each other. Finally, electrons are in continual motion. Each of these forms of motion involve kinetic or potential energy, and these energies in sum make up what we call the internal energy. Therefore, at the macroscopic level, the total energy of the system is the sum of the system kinetic and potential energy and the internal energy. It is interesting to work some numbers. This slide shows the kinetic and potential energy for a 1 kilogram control mass traveling at 10 meters per second at 10 meters above ground. The kinetic energy is 50 joules and the potential energy is 98 joules. Now compare these numbers to what the internal energy might be. Suppose the atoms are vibrating like little harmonic oscillators with Vmax about 30 meters per second. The density of solids and liquids is about 1,000 kilograms per meter cubed. Running the numbers, we get about 100 joules. This is the same order of magnitude as the system kinetic and potential energy. This is the fact that makes thermodynamic systems work. If we can access this internal energy, either to increase it or decrease it, then there are endless possibilities for putting it to work in useful ways. For a closed system, there are two ways to access internal energy: work and heat transfer. While work and heat transfer involve force acting through a distance, you may think of work as an organized, coherent action. For example, the force applied to a piston due to a pressure difference acts across the entire piston. Conductive or convective heat transfer may be thought of as work done at the microscopic level. Molecules in two adjacent media are striking each other randomly such that there is a net transfer of energy. In radiative heat transfer, photons are absorbed or emitted by the system mass at the molecular level. Both work and heat transfer are processes and have dimensions of force times distance, or energy. In the SI system, the unit is joules. In the English system, the unit is BTUs. The first law for a closed system can be written as shown in the slide. Note that we have again written it as a balance relation with change of state on the left and processes on the right. The change in total energy of the closed system must equal the net work and the heat transfer acting on the system. For an open system, we must take into account the effect of mass flow into or out of the system. This is because mass carries energy in the form of internal, kinetic, and potential energy. However, it also takes work to push the mass in or out of the system. This is called flow work. Flow work is illustrated in this slide, taken from Sengel and Bohl's fine undergraduate text. To push mass into an open system requires work. The force is equal to the pressure difference across the volume times the cross-sectional flow area. The distance is equal to the volume of material entering divided by the flow area. The work is then equal to the pressure times the volume. We more commonly express the flow work on a per unit mass basis so that it becomes the pressure times the specific volume, or equivalently the pressure divided by the density. It turns out to be useful to introduce a new property called the enthalpy as the sum of the internal energy and the flow work, or H equals U plus P over rho. Then the mass flow energy transfer rate into the control volume becomes m dot times U plus P over rho plus V squared over 2 plus rho Z, which is equal to m dot times the quantity H plus V squared over 2 plus rho Z. We now have everything we need to write the first law for either an open or closed system. Here we show the result for an initial final value problem or a general rate problem. You might review the various forms of the first law as discussed in any undergraduate engineering thermodynamics textbook. When we solve thermodynamic problems, we use the first and second laws and property relations to provide relationships between processes and states. In general, a thermodynamic analysis means finding the values of all the processes and states involved in the problem at hand. And we can only do so if the number of unknowns is equal to or less than the number of relationships we have available. So typically we try to evaluate each term in the first and second laws as a first step. For example, system kinetic and potential energy are determined from the system speed and position. Work and heat transfer are processes that we must measure or calculate in detail to know independently. Property relations must be available. They are the main topic of this set of courses, and we will explore them in detail. In the end, we may be solving for properties or processes, or both, depending on the available information about the problem. This is it for this video. Thanks, and have a great day.